Okay, so in this video, we're going to be talking about in probabilities, your unions and your intersections. And again, in case you see some symbols here, the U, that stands for union. And then an upside down U, that stands for intersection. So just to get those symbols out of the way. So this chapter focuses in on finding this section focuses on using the addition rule for disjoint events, which is also, as known as mutually exclusive events. Also the general addition rule, and then computing probabilities of an event using the complement rule. So those are the three main focuses of this section here. So the addition rule for disjoint event, two events are disjoint if they have no outcomes in common. And another name for disjoint is what we call mutually exclusive. And I always like maybe having a picture to represent what does that mean. So when we're saying that two events are disjoint or mutually exclusive, that means they have nothing in common. So in our Venn diagram down below, they don't have anything. When we look at event E and event F, they don't have any overlap. They're two totally separate circles. So that's an indicator that they're disjoint. So when you see those words, I would immediately draw a picture. And if they don't see the words mutually exclusive or disjoint, then that's probably a good indicator that we probably have some overlap. They have some things that are in common between the two events. So we would draw a Venn diagram where they have overlapping circles. Or you can even do like a two-way table where they have something in common. There's a lot of different ways to represent it. The addition rule for disjoint events says that if you have two events that have no outcomes in common, the probability that one or the other occurs is the sum of their probabilities. So more or less, when I see the probability of E or F, I can just take the probability of what is going to occur in event E and then add whatever the probability of event F is and get my final probability. That's what the addition rule says for disjoint events. Here's a specific type of probability model that comes up. Several different times. It's Benford's law, and Benford's law was basically used to kind of help in the accounting world and whether the IRS uses it or not, but even just some bookkeeping, where it was developed that certain numbers. Being the first digit of a number on an expense report or whatever, certain numbers get, used frequently. And so here we have, basically the probability of the first digits of 1 is 30% and so forth. And what they try to do is use that to try to figure out, hey, is there any irregularities in an expense report or like on tax returns as they try to analyze some numbers and doing things. So they asked us to use Benford's laws to determine the probability that a randomly selected first digit is going to be a 1 or a 2. So now these are disjoint events because we're talking about either being 1 or 2. And so they don't have anything in common. So with this one, we're basically taking the probability that the event is 1 or 2. Let me rewrite that. Or a 2. So we can technically take the probability that it's a 1, add the probability that it could be a 2, and then I can just add the two probabilities from the table. So 0.301 plus 0.176, and that gives us a grand total of 477. So there's a little bit less than 50% chance that a randomly selected first digits is going to be a 1 or a 2. But 47 to be precise. Use Benford's law to determine the probability that a randomly selected first digit is at least 6. So that's probability that the digit is at least, at least means greater than or equal to 6. So for that case, I'm looking at all of these sections here, all those together. So that means I can take the probability of a 6 plus the probability of it being a 7 plus the probability of it being an 8, plus the probability of it being a 9. And so with that in mind, oh, goodness gracious, let's line it up this way. 67, 58, 51, 46. 14, 21, 22, 8, 13, 18, 22. So there you go. So the probability would be 0.222. That'd be at least a 6. All right, some more, again, we like seeing dice. We like using coins. We like using cards. Here's the sample space of a deck of cards. Remember, you have your 4 different suits, 13 cards in each suit. The face cards are your Jack, Queen, King. So when they talk about face cards and so forth, Ace is not a face card. So now they say compute the probability of the event E being drawing a king. So probability that I draw a king, and we're just drawing it one time, so we're not doing successive events, so just one. So with that in mind, there are 4 kings, 1, 2, 3, 4 kings in a deck of cards, over how many cards are in a deck? 52. These problems always involve not using the joker, so that would be 1 out of 13. Now we have a problem where it says compute the probability of event E drawing a king and let F be a queen and G be a jack. Okay, well, great. So what's the probability that I get a king or a queen or a jack? So with that in mind, and I know they used E, F, and G, but I can just take the probability of each one. So I have 4 kings out of 52, plus 4 queens out of 52, plus 4 jacks out of 52. That gives me 12 out of 52 total. And then I can go ahead and reduce that, and that makes that a 6 out of, well, actually I can divide by 4. So that would be 3 over 13. So I got a 3 in 13 chance that when I draw a card, that it could be a face card. The general addition rule is something is where we have overlapping events, and then you can technically, if you're looking at, hey, do I have to memorize 2 different addition rules? Really, the best one to memorize is this one right here, the general addition rule, and I'll talk about it here in a minute. So the general addition rule is associated when we have overlapping events, so they share something in common. What the rule says is that if I want to find the probability of event E or E taking place, then I can take the probabilities of both of them and add them up separately, but I got to subtract what they have in common, and this is the overlap part. So this is the middle part. This is technically the P of this would be this inside section right there. And again, you can use this as the only formula you memorize for the addition rule, in my mind, just because if they don't overlap, then that means I'm subtracting 0 at the end. So because the first part is the addition rule that we saw up above. All we're adding in it is a stipulation of we got to subtract off the overlap. Because if we don't do that, then we end up using the middle numbers twice. So we just got to subtract off what's in the middle. That way it's only being used once in the process. So suppose a single card is selected from a standard deck of cards. Compute the probability that the event E draw a king or F draw a diamond. And again, these are not mutually exclusive events. They are overlapping because we do have a king of diamonds. So what's the probability I do a king or a diamond? Again, notation-wise, P of E or F. So with this in mind, we can take the probability of a king plus the probability of a diamond. But I got to subtract off the probability of a king and diamond. Now, I don't have these things in probability. I have them in more of a frequency thing. So I'm going to write them as fractions, so they're in the probability settings. So there's 4 kings out of 52. There are 13 diamonds out of 52 cards. Now, we do have a king of diamonds, so I got to subtract off that 1 king of diamonds. That way I don't use it twice. So 4 plus 13 is 17, minus 1 is 16, so that's 16 out of 52. Reduce it down, divide top bottom by 4, and I get a 4 in 13 chance that I will get a king or a diamond when I pick a card. All right, so now we get into some more examples of using the general addition rule We do need to, and I'm going to do this on a separate calculator, get some totals here. That because as we start asking some of these conditions here, so real quickly, I'm just going to add up and total stuff out to the side. That's an 86.1, 125.3, 15.2, 28.2, and then 5.3. Adding down, let's go with calculator on that one. 46 plus 63.3 plus 3.3 plus 12.1, and then another 2.2. That got me 126.9. The next column, 40. And again, we want to have these total. I'm totaling them out now just in case they ask me any type of arrangement of trying to figure out the probabilities. So that's why I'm going through the process now of doing that. So. That looks like 133.2. I'm going to add it to that 126. And that gives me 260.1. Now, this is in millions, so that means I would actually move the decimal point, and so we're not worried about it being a decimal there. But I do want to make sure my vertical column adds down that I have in blue to that same number. That way I know I did my math right and didn't have any happy fingers in the calculator. And I got the same number, so good. So I know that added up. So again, that would be technically saying like 260, and then in millions. So I'd multiply that by a million. So then that would be 1, 2, 3, 4, 5 zeros. So that's what this number would actually look like as a whole, 260 million. All right. So determine the probability that a randomly selected U.S. resident is 15 years or old or older is male. It's probability that we have a 15-year-old, it's 15 years or age or older and is male. So with that in mind, that's what I have as my, these are all 15-year-olds in the process here. So we know for males, there is 126.9, and that's again in millions, is technically what we say. We don't have to put it out with all the zeros. Divided by our total. How many total do we have in our thing? So I'm just going to take 126.9 and divide it by 260.1. And the probability is when I do that dividing, 126.9 divided by 260.1. Gives me the probability is going to be 0.48788. So, we're looking rounded to the fourth decimal, 0.4879. So that's the probability of being a 15-year-old older is male. Determine the probability that a randomly selected U.S. resident 15 years or older is widowed. So now that changes. They're saying widowed. Well, that would be this row. And they didn't say if it was male or female, so we're combining the two of them. So in this case, we would want to take the 15.2 and divide it by the 260.1. So 15.2 divided by 260.1 gives me approximately 0.0584. So there's a 5.84% chance that we randomly selected U.S. resident who's 15 years of age or older is widowed. Determine the probability that the randomly selected U.S. resident who's 15 years or older is widowed or divorced. So I get to, in this case, take the probability that it's a widow or divorced. So now I get to add the probability of being a widow plus the probability of being divorced. So I'm going to set up one fraction here. So what was the number for widowed was 15.2. The number of divorced was 28.2. So 15.2 plus 28.2. And then that gives me 43.4 divided by 260.1. Divided by 260.1. and that gives me, it looks like 0.1669 if we round to the fourth place. So there's a 16.69% chance randomly selected person is a widow or divorced. Now, determine if the probability that a randomly selected U.S. resident is 15 years or older or is male or widowed. Here's the thing here. So probability male or widowed. Now, the previous ones, we didn't have any overlaps because, again, we were using the row and columns like you're either widowed or you're divorced. You can't be, it's they're kind of broken down. There was no overlap in those categories. So on this one, there is an overlap because you could be male, you will be male and then also divorced. So there is some overlap there. So this one I have to use the general addition rule. So the probability of male plus the probability of being widowed, because it didn't say, female. It could be a female widow. Doesn't matter. But I have to subtract off the probability of being a male and widow, because again, we're already using that one right there, that event in the male category. So as we look at our numbers here, it was 126.9 out of 260.1. Widow, we said, was 15.2 out of 260.1. I got to back off the male widows. There was 3.3 male widows. And then now I can go ahead and do the math and divide. So looking real quickly, 126.9 plus 15.2 minus the 3.3 overlap gives me 138.8 out of 260.1. And that is approximately 0.5336. All right, the complement of event. So we're letting S denote the sample space for our probability. So that's that whole entire box we see down below. E is our event, and the complement event is denoted by the E to C to the little c power. Sometimes we also see a little squiggly, and like this, and that also stands for not E, so not event E. If E represents any event and E of C is its complement, then the probability of the complement of E is basically 1 minus the event, the probability of event E taking place. This comes in handy when they ask us to, you do it like an at least or an at most kind of thing for probabilities, and we're like, hey, well, I can, instead of adding up a bunch of things, I can just do 1 minus the opposite of that event. So that's what we'll get practice in doing here. According to the National Gambling Impact Study Commission, 52% of Americans have played the state lottery. What is the probability that a randomly selected American has not played the lottery? So again, if we say our event E is equal to played the lottery, then E to the C, or E complement, is equal to not played the lottery. Now, they asked me to figure out what is the probability that they did not play the state lottery. So what's the probability of E to the C? E complement. I can, again, use the complement rule where I can do 1 minus the probability of event E, which is, we've defined event E as being played the lottery. So I can do 1 minus 0.52, and that would give me 0.48. So there is a 48% chance that a randomly selected American has not played the state lottery. Last question in the video here. Again, we got to get some totals here in order to kind of figure out what we're doing. Now, you could, if you want to, once you find a total, we could go through, find the individual probabilities for each of those. Now, they did tell us this one is in thousands. So, like, for example, each one of these numbers we would put 3 zeros after, and that to let us know how many households, or people earn that amount of money. So there's roughly 7,804,000 people that make less than $10,000 and so forth. So they asked us to compute the probabilities that a randomly selected household earned in the following incomes in 2017. So they asked us to do probability. The probability. Oh, sorry, my pen's acting a little quirky. Probability of that it's greater than. Oh, shoot. All right, we're going to have to change tactics here. Probability that X. Let's go to. My apologies. My pen died at the same time. Draw with touch. Okay, we're going to go with using the fingers on this one. That X is greater than 200,000. All right. So with that in mind, well, we do need to get the totals here. We know that there is this last category is what we're focused in on. So that's our top number. So there's 8284 over. Now again, that would be 8,284,000 people. So I need to find out a total here real quick. So let me go ahead and add up these numbers. Almost there. So that tells me the total was 109,013. So about 109,013,000 people were in this. United States or people were in this data collection for this survey to get this numbers here. So 109,013. And now we go over here and we go, all right, what is 8284 divided by 109,013? So the probability of randomly selecting a person that makes more than 200,000 or more is 0.07599. Again, that would be basically 0.076 because we would round and to the fourth decimal, and so it's about a 7.6% chance that a randomly selected person makes more 200,000 or more, or a household does. So now part B says, what's the probability that less than 200,000? Well, we could, if we wanted to, we could we could go through and add up all these, and if there are probabilities, we could add up all those probabilities, but that's just a lot of work. This is where the complement rule comes into play. This is basically, not more than 200,000. So in this case, we can use the complement rule and say, okay, I just need to do 1 minus the probability that they make more than 200,000. We already have that answer. We already have that probability. So we're going to do 1 minus 0.07599. Again, if we used all the decimals on the calculator, that would be the most accurate thing to go through and do. But I'm going to do 1 minus 0.07599. I put the 99 back in there for this part because we want to make sure we're accurate enough. If we use my rounded one for this answer, then we're going to be off by probably the adjustment key for grading. So 0.92401. And I'm going to go back here real quickly. I'm just going to do it on my calculator with that big long decimal when I did the first division to see if there's any difference. Now, the only difference is it's actually 0.924009. So again, if they're having us round to the fourth decimal, we should be fine. I have it out to 5 decimals when I put the 99 back in there. So we would be safe saying that it's 0.9240 rounded to the fourth decimal. What is the probability that it's at least 10,000? So as I try to get another part to go here, probability that our event is at least, which means greater than or equal to 10,000. Well, again, that would cause me to add up all these and those numbers that I just circled there, all of those together, and divide it by the 109,013,000. Or I can use the complement. So again, basically, if I do 1 minus that event, then that tell me what all that other stuff adds up to be as a percentage. So I'm going to do 1 minus the probability that X is less than or equal to 10,000. That represents that first cell. So that would be 1 minus, and then we'd have 109,013 is our denominator. Go back and get our numerator, 7804. 7804. So I'm going to divide that out real quickly. So 7804 divided by 109,013. So this is 1 minus 0.0715877,923. And I'm going to go 1 minus that answer on the calculator. And that gives me 0.92841. So 0.9284. Very similar to the last answer we got up there on the previous one. That's just because there was just almost similar numbers in those two categories. You know, there's not much difference between 7804 or 7,804,000 and 8,284,000. So there's about a 400,000 difference there. So that's why our percentages should be about close on those two answers there. So again, complement rule helps when you got to add up multiple things together. Sometimes it's easier to do 1 minus that event not happening. Is what's nice to do. Again, be careful as you do your different probabilities. Be careful with using your addition rule. Again, I would just memorize the general addition rule, and if they're not overlapping, then I know it's -0 at the end. But then it's just one less formula I got to memorize. I just know if they're separate circles, I got to put a -0. So makes it a little bit easier when we're doing a lot of probabilities.